Before I begin, the usual disclosure that these are my personal opinions and they don't necessarily reflect those of my employer. So the Akka Streams Akka Streams API is an efficient API, and as long as you're not constructing extremely complex graphs, it's pretty easy to get impressive throughput. But there are situations, however, where careful attention to how the stream is actually executed can greatly improve the performance and throughput, as well as the scalability of your application. And that's the focus of this presentation. And I'm going to look at 3 topics. First is maximizing the throughput of an individual stream. Second is how to partition a stream in order to maximize throughput. And then finally, how to partition a stream for scalability as well as high availability. Now it's not an introductory talk to Akka Streams. I assume you have some working knowledge of Akka Streams, but I think even if you haven't touched them, I think the talk will still be digestible. If you are looking for an introduction to Akka Streams or the motivation for using Akka Streams, check out this presentation of mine from Scala Days or these 2 blog articles that motivated that presentation. So before I dive in, I'll just provide a few examples of streams to kind of motivate the problem. So streams can be ephemeral. So that might be something like a source that emits a fixed set of elements, like a list, that you then filter out some elements, maybe perform a mapping into a different data type, and then send those elements to a sink, like a file or a database or an HTTP response. You can also use a stream to process the results of a future, such as a request to a database. Or you can also use streams to provide bounded resource constraints. So say for a large workflow, you might want to limit the number of asynchronous operations that are happening at any one time. Streams can also be unbounded. So consider a durable message queue that receives an unbounded stream of messages from IoT devices, application log messages, or business transactions. It's pretty common to have stream processing applications that do data transformation, enrichment, digital twin modeling, inventory management, machine learning, anomaly detection, and these streams tend to run forever on that unbounded stream of messages. Akka Streams can also be used to run continuous ETL applications, and the Alpaca project provides a rich set of sources and sinks that'll connect different systems. And even individual services or devices can have unbounded streams of messages, like an IoT device that's sending telemetry over a WebSocket connection, which is actually modeled as an unbounded stream. So whether a stream is ephemeral or durable, bounded or unbounded, the strategies to improve the performance basically boil down to the following. I want to minimize latency, so the kind of end-to-end latency of any single message, maximize the overall throughput of the entire stream, and maximize scalability through efficient use of resources. So a reminder of the 3 topics that I'm going to cover, and just a note on the examples. The examples I provide are all like little toy examples rather than something that's super elaborate. And they're actually examples you can play with yourself to see the impact of changing the streaming model that you're using. Okay, the first topic is maximizing the throughput for an individual stream. And the most fundamental thing to understand is asynchronous boundaries. So consider this simple stream with a source, and then a couple of map stages, and finally a sink. In code, it looks like the following. The source emits 1,000 elements, followed by the 2 map stages. And the messages are then sent to a sink that simply ignores them. And the spin function that I'm using in the map stages looks like this. And it's just designed to waste CPU for 10 milliseconds, and then pass the value through. Okay, so back to the concept of asynchronous boundaries. Akka streams are executed by actors under the hood, and you really don't need to know about this or pay attention to this until you want to start improving the performance of a stream. Operator fusing is a technique that they use to execute adjacent stream stages on one actor, and this avoids the overhead of message passing across actors to increase the performance. So in this example, it means that the 2 adjacent CPU-bound map stages cannot execute in parallel unless we take additional steps. And the way to allow these 2 adjacent stages to execute in parallel is to insert this asynchronous operator, which inserts an asynchronous boundary. And the stream will be executed in 2 actors now with message passing across that asynchronous boundary. And what this looks like in code is instead of having the adjacent map stages, they are separated with the asynchronous boundary with the async operator. And this stream will execute twice as fast now, just because it can execute those 2 stages in parallel. Another way to introduce parallelism is through the MAPASYNC operator. MAPASYNC can be used to execute a future and then emit the completed result of the future to the downstream. And you can set the upper bound on how many futures the stage is executing at any one point in time by adjusting the parallelism of the MAPASYNC. So returning to the stream that we just looked at, this stream will run equally fast if instead of using the asynchronous boundary, we capture that spin function in a future and then use MAPASYNC. So this is a very important thing to understand, is what's the difference between async and MAPASYNC. So revisiting the original expression of the stream when everything was in one asynchronous boundary, inserting the asynchronous boundary with the async operator introduced parallelism by executing the stream in 2 different actors. MAPASYNC can achieve equal performance, but what it's doing is achieving parallelism not through an asynchronous boundary, but by executing the work in a future, potentially on a different thread. And these 2 concepts can actually be combined. So, so taking that expression of the stream using MAPASYNC, you could insert an asynchronous boundary between the 2 MAPASYNC stages. And what this would look like in code is similar to before, using the MAPASYNC operator between those 2 adjacent stages. Now in this case, all this does is add additional overhead. This doesn't actually improve the performance of the stream, but there are cases where this can improve performance. However, adjusting the parallelism of the MAPASYNC here will improve the performance. So if we set it to 2 instead of 1, this will allow the stream to execute twice as fast again, four times faster than the original expression of the stream, assuming that there's enough CPU. And note that that's a parallelism that you could not achieve with the async operator itself, just because you can't achieve that level of parallelism by inserting it. So those are your 2 tools for playing with parallelism. And so an important question becomes how to tune the parallelism of MAPASYNC to achieve maximum performance. So I already showed how easy it is to adjust the parallelism, say, from 1 to 4. And in code, this looks like something like the following, going from a parallelism of 1 to 4. And this allowed the stream to run 4 times faster. But how do I know it wouldn't run 8 times faster if I put 8? So the story is basically for a CPU-bound workload like this spin function that I've been using, you should set it based on the number of cores that are available. But of course, you need to balance this decision by the composition of the stream. If you have 2 or 3 MAPASYNC stages, you need to consider what they're all doing. Or if your application is running more than one stream, you need to balance that trade-off. But assuming that you only had, say, 1 MAPASYNC stage and all available cores, set it to the number of available cores for a CPU-bound workload. But it also raises the question if it ever makes sense to do something like this and set it to 1,000. And the answer is actually yes. So far I've looked at this CPU-bound workload. But consider this non-blocking workload that would simulate, say, a call to a web service or a database, something like that. And that's non-blocking. So it creates a promise, creates a random number of milliseconds between 0 and 100, schedules the promise to complete at the end of the timeout, and then just passes the value through again through the future. So this stream runs 1,000 of those non-blocking calls using the MAPASYNC parallelism of 1, and this will take somewhere between 50 and 60 seconds to execute this stream. But with a parallelism of 1,000, it'll complete in approximately 100 milliseconds. So that's 3 orders of magnitude faster, and it's going to run all of those non-blocking calls at the same time. And so that's a situation that you could have if you're calling some very scalable web service, and you can just run all that work at the same time, and you're doing very little work locally. So you can basically set the parallelism to what that other service would tolerate. So this async stuff seems really great, so let's put it everywhere. And this isn't always advantageous, as you can probably imagine. So consider these 3 case classes that simply wrap an integer, and this stream of 1 million elements that just maps through each of the case classes. If an asynchronous boundary is inserted between each stage, it will execute twice as slow. Similarly, if each mapping is executed in a future, the performance will be equally poor. And here I'm using future apply on purpose rather than future successful. So the reason is that the first implementation introduces the overhead of message passing through actors across that asynchronous boundary again. And the second one introduces the overhead of executing the future on another thread. So you need to use some caution. The parallelism can't be introduced blindly. The overhead must be justified by the performance gains that you're going to get. There's also an unordered version of MAPASYNC that can improve performance in some situations. So a really powerful feature of MAPASYNC is that it emits elements downstream in the same order that they were in the upstream, no matter which order the futures complete in. And this is really important when you need to maintain ordering guarantees in your stream. But if the workload is non-uniform, it can lead to head-of-line blocking if one future takes a really long time to complete. And if you can relax ordering guarantees, MAPASYNC unordered can be used to improve the performance of these streams by emitting elements downstream as soon as they complete and then starting the execution of the next future. And to demonstrate this, instead of that spin function I was using so far, consider this non-uniform version that's going to pick a random number of milliseconds between 0 and 100 and then consume CPU for that long. This stream that runs that non-uniform CPU-bound workload will run faster if the MAPASYNC stage is replaced by the unordered version. And the more variation that you have in that non-uniform workload, the more dramatic this effect will be. And it's especially dramatic if there's a really small number of events in the stream that take an extraordinary amount of time to process. Now, buffers can have a really subtle effect on performance or a really dramatic effect on performance, depending on the composition of the stream. And they take a few different forms. So when you insert an asynchronous boundary, the stream is now using message passing across that boundary like I described earlier. And there's actually a small buffer of 16 elements, which is essentially the actor's mailbox. And this can indirectly improve performance when workloads are, again, non-uniform by keeping the downstream saturated. So here's an example of 4 MAPASYNC stages that each run some non-uniform workload. This stream will complete faster if an asynchronous boundary is inserted between each stage. Now, the improvement in performance here is not coming from the asynchronous nature of that change, but just from the fact that there's the 16 element buffer between each stage that ends up keeping the stream more saturated. And you can actually achieve equivalent performance by inserting a buffer. So here, there's no asynchronous boundaries here. It still has operator fusing. It's executed on one actor, but it'll have equivalent performance. Another place where explicit buffers are really useful in saturating a stream is reading messages from a work queue or a message bus. So if there's some messages that are much, much larger than others or take significantly longer to process in the stream or transfer from the upstream, a buffer is really helpful for saturating the downstream rather than sitting idle waiting to fetch the next message. So here's an example of a Kafka consumer. And depending on how the stream processes messages, inserting an extremely large buffer sometimes can really improve performance by saturating the downstream, if it's non-uniform again. But just like we saw with indiscriminate use of async, indiscriminate use of buffers doesn't end up helping in terms of performance. So take this stream with a couple of MAPASYNC stages. If adjacent stages perform relatively uniform workloads, then inserting a buffer is not going to change the performance. It's just going to consume more resources. The performance is going to be dictated by the slowest processing stage. And the last topic with regard to the performance of an individual stream is the handling of exceptions. The default behavior when a stream throws an exception is to stop the stream. But you can define this decider mechanism to have a few different behaviors, including restarting the stage and continuing processing, or simply dropping whatever that message was and keep going. And so the decider allows you to set those rules, and it also allows you to inspect the exception and take different actions when it's thrown. So consider the following stream that basically throws an exception for almost every element. Maybe this is some legacy API that still throws exceptions that you have to deal with. from like a message parsing library, something like that. So this stream will run 2 orders of magnitude faster if those elements are filtered out in the stream rather than blowing up the call stack and doing that filtering in the decider. And of course, there's many ways to filter streams. Here doing it with collect, but there's a whole bunch of different stream compositions you can use for filtering. Another approach, and I think arguably a better approach, is to model those errors as data. This is actually, it's especially important if you're doing something like reading from Kafka and you need to manage your consumer offsets downstream. You can't necessarily throw away all your errors. Your errors need to make it all the way to the end of the stream for handling. So modeling errors as data and perhaps even sending those to a different sink for handling can often improve the performance rather than throwing exceptions to the decider. Okay, to summarize maximizing the throughput of an individual stream, you want to increase parallelism, and the tools for doing that are async and MAPASYNC. But you don't want to necessarily increase it too much. Be cognizant of your resources and how you're using them, and then operator fusing is there for a reason. Don't necessarily destroy that performance benefit. For non-uniform workloads, you can insert buffers, and you can also relax ordering in some situations to improve performance. And definitely avoid exceptions, either use filtering or model errors as data. And this is a really important point that I want to emphasize, how easy it is to experiment with improving the performance of your streams, right? We didn't have to write reader-writer locks or introduce new threads or pub subs or queues, anything like this. You insert an async stage, increase the parallelism, insert a buffer, insert a larger buffer, these kind of things. Rerun your benchmarks, see if performance improves. You don't need to write hardly any code. Okay, the second topic is how to then partition a stream to maximize throughput. And I'll look at broadcasts to begin. Broadcast is a way to partition a stream by sending every element to independent downstreams. So every downstream is going to get the same stream. So in this example, the downstream performs a mapping before the streams are then merged back together. And this is what it looks like in code using the graph DSL. So we set the number of partitions to 4. Whoops. Create the broadcast stage with 4 partitions. Then a merge stage that accepts 4 inputs. And then define the downstreams here that each have one of those map stages that waste CPU in the spin function. And this graph can be run with 1,000 elements, and it looks like the following. Now, just as important as understanding asynchronous boundaries for individual streams is understanding them when you're partitioning streams. So this graph, broadcast to 4 downstreams, will run 4 times slower than just running one of the downstreams in a single map stage. And the reason for that is it's all running in one actor. So to improve the performance, it's equally important to apply asynchronous boundaries when you're partitioning streams so that the downstreams can run in parallel on different actors. And returning to the graph definition, achieving this performance boost is as easy as before, just inserting that asynchronous operator. Another way to partition for performance is using the partition operator. And this sends individual elements to one downstream based on a custom partitioning function. In this case, sending 1/4 of the messages to each downstream. So it's common to exclusively partition a stream based on a unique identifier or a consistent hash of an address, something like that. And that'll maintain total order within each partition, but it won't necessarily maintain total order across the stream. And then how do you pick your partition size? Well, it's kind of back to what we were talking about with MAPASYNC earlier. If it's a CPU-bound workload, you might want to choose your partitions relative to the number of cores you have. If it's not CPU-bound, you may be able to increase your number of partitions to be quite large. So in code, broadcast looks very similar in terms of the graph definition, selecting the number of partitions and defining the partitioning function. And again, taking care when we're defining the downstreams that they have asynchronous boundaries. So with each downstream only processing 1/4 of the elements, it will complete in 1/4 of the time of the broadcast example that we just looked at. Now, a really interesting way to partition streams, but it's only applicable to a subset of workloads, is balance. So a partition element that we just looked at, it's going to back pressure when the currently selected downstream is backpressuring. So in situations where downstream workloads are non-uniform and the total order of the stream or an individual partition is not required, balance can be used to saturate the downstream, using the downstreams as like a pool of available workers. And it'll emit to the very first available downstream. And it's not going to backpressure until all of the downstreams backpressure. So this non-uniform spin function will help demonstrate this. So every fourth element takes an order of magnitude longer to execute. And then the definition of the balance is similar to what we've already seen with the graph stages. Again, with the async. So running this graph using balance will execute 3 times faster than using partition. But of course, being able to use balance depends on the workload being non-uniform and also being able to relax ordering guarantees. So if you need ordering, this model of stream partitioning is not going to work. Now, Akka Streams has a bunch of dynamic stages as well. There's too many to detail in this presentation. And their applicability is really workload dependent. But I'll give you a flavor of a few of them so you understand the performance considerations, starting with group by. So it's similar to partition in that demultiplexes a stream into a set of independent downstreams using a partitioning function. But it differs from partition in that it emits a subflow rather than the more common source or flow. But it can be used to consistently partition a stream. What it looks like in code is a group by element that takes a partitioning function similar to the partition we already saw. Then it wastes some time, wastes some CPU in a map stage. It's equally important to insert asynchronous boundaries here. Otherwise, the substreams will not execute in parallel. And then substreams are completed by attaching them to a common sink or by merging them back together. And this example uses merge substreams to merge them back together. Now, a few caveats about group by. Group by is dynamic. So if there's a huge number of partitions, like you're partitioning based on a session ID or something like that, it can consume significant resources, and they'll be continue to be consumed until the stream is stopped. There's no way to recover them. So it's better to do that kind of processing by interfacing streams with actors and then controlling the lifetime of resources by stopping an actor after an idle timeout, something like that. And the second thing is if you try and limit parallelism here, with the merge substreams with parallelism, and that's less than the maximum number of substreams emitted by the group by partitioning, the stream can deadlock. And split when is somewhat similar. For example, it allows splitting a stream into substreams based on a predicate. So this might be something like a windowing function or a watermark. And its effect on performance depends on the size and the number of substreams you're kind of able to emit from it. And lastly, the last dynamic stage I want to talk about is broadcast. Broadcast allows a stream to dynamically subscribe to a source, and new streams can be added on the fly, joining the stream of messages in progress. And this is really useful for subscribing streams and fanning them out to something like, say you're using server-sent events, WebSocket, gRPC streaming, something like that. But an important thing is that the rate, the producer rate will be automatically set to the lowest downstream consumer rate. So an important thing to do is to insert a buffer stage to decouple the downstreams from the broadcast hub. And if the buffer fills up for a downstream consumer, you could just stop dropping those elements, perhaps. Or you can even fail that slow or idle downstream consumer so that you recover resources and that you don't impact any of the other streams. Okay, to summarize partitioning for throughput, it's very workload dependent. Your workload needs to fit the model. You can broadcast the whole stream and run independent streams off of it. You can partition to divide and conquer, balance to have this pool of workers model, and then there's these dynamic stages that basically run independent downstreams. Okay, so the final topic is partitioning for scalability and high availability. And this is only a very small part of the presentation. I'm not going to dive deep at all. But these ideas are really, really important if you want to build systems with huge scalability and reliability. So the first technique is to scale streams by static external partitioning. So for example, a stream might be processing files from a dedicated S3 bucket or from the file system of an IoT device. And as you have more devices or more buckets, you just run more streams, one dedicated to each. And the streams run independently and most likely on different computing resources, which provides great scalability. And it also provides a lot of reliability because you have isolation across those streams. Another approach is to dynamically partition streams. So imagine an ETL application reading from a work queue or a consumer reading from Kafka, something like that. If the stream in one of those applications is not enough to keep up with the workload, even after you've applied all the techniques that I've talked about so far in this presentation, you could scale the stream up dynamically, running more workers to satisfy the workload. For example, by scaling the number of pods deployed on Kubernetes. And after scaling up, a Kafka consumer is going to rebalance those partitions across the consumer group. Or if you're reading messages off a work queue like SQS, now you have more workers reading off that same queue. And a final way to partition streams to provide great scalability as well as fault tolerance is to use Akka cluster sharding. And the idea here is to let an individual actor run an individual stream or group of streams. And maybe that's a stream interfacing with an individual IoT device. And then you let Akka runtime scale this to millions, sharding those actors across a cluster of coordinating machines. And this provides tremendous scalability through parallelism and elasticity, and also fault tolerance, because if one of those servers fails, the actors on that server will be rebalanced to another server, and then the streams that they're running will be restarted. And this is a really, I use this a lot. This is a very useful way of building applications that model entities, especially in IoT, that incorporate streaming workloads as well as state. It's well beyond the scope of this talk to get into this, but if you're interested in this subject, you can see this talk of mine from Reactive Summit on how to incorporate actors and streams in this manner. Or this 4-part series of articles that I wrote that basically motivated that talk. It's worth noting that these articles, the ideas in these articles still apply, but I think they're 3 or 4 years old, so they predate Akka typed. I would definitely use Akka typed to implement this kind of thing. So to summarize partitioning for scalability and high availability, use static external partitioning for static or declarative deployments, dynamic external partitioning through consumer groups or work queues, or dynamically with actors and cluster sharding. And what these do is run the streams independently, and you let the runtime recover from failures or provide dynamic scaling of your streams. Okay, those are the 3 topics that I wanted to cover. The main takeaways, you need to understand the dynamics of your streams and your workloads, as well as the external systems that you're interfacing with. Introduce asynchrony to maximize concurrency, buffers to avoid starvation and to provide decoupling among stages. Watch out for head-of-line blocking. Partition the stream internally for concurrency, and partition streams externally for scalability and high availability. And again, I can't emphasize enough how easy it is and how reliable it is to experiment with these techniques, run your benchmarks, adapt, and improve performance. That's me on Twitter. If you want to stay in touch, that's my blog. I write 1 article a month. There's a lot of stuff on Akka Streams on there. There's also stuff on managing teams and where I think the industry is heading in terms of stateful serverless and these kind of things. If you want this presentation in written form, refer to these articles. I got 1 minute for questions. I think there's a microphone.
Okay, just a really foundational question. Let's say you have 2 operations you want to run in parallel, but they both need to complete before you can proceed again. And then right after that, you have another 2 operations that need to run in parallel. How would you express that with map and map async and all that?
It sounds like you're going to need bifurcation and merging of your stream, but that's totally possible. You need to express it in a graph, basically.
So you'd have to use a graph for that. Yeah. Okay.
Hi. Why is it that keeping the downstream saturated leads to better performance? Is it that
otherwise it's going to be sitting idle? I think the Kafka example is a really good one. That's the first instance that I encountered it. We had an extremely large message. So even though the consumer itself had a small internal buffer, every once in a while there would be this enormous message that took a while to transfer. So the stream is sitting idle downstream doing nothing, and you're waiting for this message to come across the wire. But if you keep the downstream busy while you do network I/O in the background such that you have this, you're accumulating your messages upstream, then the downstream can always be busy.
So it's a statistical multiplexing question, basically, right?
Yeah.
Cool, thanks.
Do you ever find there's cases where you drop into custom graph stages to optimize further than the DSL allows?
Very rare, and I can't think of ever having done it for performance reasons. It's more for expressing business logic reasons. I can't recall ever doing it for performance, and even for business logic, it's pretty rare. I'm happy to stick around for questions too. Go on.
Okay, great. Thanks,
Thank you.
Colin.